right, so yesterday we got to see a running model that had a wet well, some force mains, and pumps. And we kind of looked at what data we needed to input, and we saw what kind of results we got. So let's take a look at how this is handled. If you're using SewerGEMS, you will notice that the different solvers that are within SewerGEMS handle pressure and pumps differently. We went over this in some detail, but we'll focus now on just the pressure part. Our recommendation is that you're doing a lot of pressure, booster stations, pump stations, grinder pumps, that you stick with the GVF-Convex solver, which is the one found in SewerCAD, because it is the most appropriate for pressure applications. That is because it uses a true pressure engine, which is the same found in WaterCAD and SewerGEMS. The explicit and the implicit solvers use a method called the Displacement slot for simulating pressure. I'll show you in a bit what that means. But with that, you can't see the system head curve or the pump operating point. And that's actually very important, especially if you're tasked with selecting the right pump for your application. So we're going to take a look at that in more detail now. Here's how the GVF-Convex solver handles the pressure hydraulics. It uses different head loss equations like Hayes and Williams, Darcy Westbach. Typically in the US, you'd be using Hayes and Williams. And the energy that gets added to the system is added by means of a pump. You can have, most of the time, it's centrifugal pumps. And the amount of energy that a pump adds, we call a pump head. And as we saw yesterday when we double-clicked on our pumps, we could see that one of the requirements was that we entered a pump curve. And if you look at this, it's flow versus head. So what does that mean? That one pump can operate in different ranges, right? So I'm going to grab my pen, and a pump is typically designed for what we called a design point, typically right around here, which happens to be the most efficient point. But that doesn't mean that it cannot operate in other places like these. So it can do that, but it will not be as efficient. And when I speak about efficiency, I mean like efficient use of the energy that it is consuming. Okay, so as long as we are aware that we can operate anywhere along that black line, but we want to always stick to the design point, then that's pretty much the gist of all we need to know about pumps. So what is a pump characteristic curve? It shows us a relationship between the energy added, remember the energy is the head, and the flow that can be passed through the pump. And the pump head is the difference in the head from the suction to the discharge side of a pump. So when we enter the pump element in SewerCAD, we just see one drawing of a pump, but really it's kind of an element with a suction and a discharge. So in fact, when you look at the results, you can see what was the head at the suction and what was the head at the discharge end of that one element. And that is what is reported as pump head. Okay, so, I see you here, Lee. Welcome. So that was the pump curve, and the pump curve is unique to your pump. Now the system has its own curve. It's called the system head curve. This doesn't have anything to do with the pump, okay? We just happen to combine those two, the pump characteristic curve and the system head curve, to find where the pump is actually operating. But this is what I was telling you that we don't get if we're using the swim or the implicit or explicit solvers. And why is this important? Well, the system head curve represents how our system responds to a range of flow rates. So here's an example. Let me see where my pointer went. If we know we have a wet well here, and we know we have to bring the water to the top of the hill at this discharge manhole, well, it isn't going to happen without help, right? So we know we have to put a pump. But how big of a pump, or it's always a question, right? Well, that depends on a few things. First, the elevation difference between the suction and the discharge. So that difference in elevation is what we call the lift. So we know we have to at least provide that much energy, right, for the lift. But in addition to that, there's going to be friction head losses that happen in the pump that connects the two, right? And also, if it's a very small pipe, like small diameter pipe, more head losses. So basically, how much work, how much friction do we have to fight to get there? And that is what you see here in this part of the curve called the head loss. So if you have to just pump a little bit of flow, then mostly the head that you'd be providing, it's the lift. But as the flow increases, you're trying to put more water through that pipe, then there's going to be more friction, therefore more head losses. So a typical system head curve would look something like this. And the steeper it looks, it means the more head losses, right? The flatter it looks, it means there's barely any resistance or any head loss. And every system is unique. Because, again, the pipe diameters, pipe materials, roughness, coefficients, whatnot. All right, and why do we care about those two? Because if we superpose the two, this point right here where they meet is called the operating pump, the operating point. So, hold on, is there a question? Okay, so this pump operating point basically is the point where the pump is going to operate at a flow and head that satisfies both the pump curve and the system curve. Okay, all right, so do we only need to care about that? Well, mostly, but not really. We also need to look at other things like basically, when you get a pump catalog, there's a bunch of curves there, and what do they mean? What are they for? Let's see if we have, no, I thought we had a picture of it here, but we don't. But typically, you have, the same graph that we had before, where we had the flow here, and we had the head, and we have our pump curve. But we also have another curve that's very important, which is the efficiency. We'll focus on those for now, because the efficiency, again, tends to be highest at the design point. So if you just went by your pump curve and your system curve, let's say it said, oh, your operating point is going to be right here. But then you see, wow, this is not the most efficient point. Yes, my pump can operate there, but it's not efficient. And the problem with operating in a point of poor efficiency, it's again that you're just paying a lot in electricity for a pump that's just, you're pushing more flow at a lower head than where it's supposed to be operating at. So we always want to be kind of on the cusp of the efficiency. And then there's another very important information, which is the net positive suction head. What happens with pumps is that if there isn't enough head on the suction end of your pump, there might be cavitation. So basically, it's not just a little bit of negative pressure. It's actually so low, the pressure, that the water has turned into vapor, and it creates these pockets that damage your impeller, your pump's impeller. So you never want to really get there. So the manufacturer tells you, okay, I'm going to tell you what is the minimum suction head that you need to have so that we don't have cavitation. Okay, so you always want to be checking for that net positive suction head. All right, so now that we understand that a little bit better, how do we go about selecting the best pump? And good pump selection really involves picking a pump for which the design flow, which we get based on projections, right? So we figure out how much flow this is going to have to pump. So we find the pump that has the design flow equal to the operating point, right? So that's kind of like our first place. And then we also look at our efficiency curves, and we say, okay, this is the point where it's most efficient, and that's the pump that I'm going to go with. So that's for a typical centrifugal pump. But nowadays there are a lot of these variable speed pumps. So the difference between them, it's that a centrifugal pump, when it's on, you know. If the needs of your system change, then you can't really alter that pump, you know. It's just always going at the same speed. And if you have a lot of changing conditions, then you know that pump might be too big for certain situations and might be just be okay for others. So to address that problem, we came up with variable speed pumps. I mean, we didn't, you know, the manufacturers came up with that. And the idea there is that you have one pump that by changing the electrical input can operate at different speeds. So when it operates at a slow speed, it actually has a pump curve similar to like a small pump. But when you increase the speed, the pump curve actually looks like a bigger pump. So it's really great because it can modulate itself to meet whatever needs you have. So a lot of people rave about them because you know, they're just like having multiple pumps in one. And we can model those in the software, and this is actually what they look like. So when the relative speed, this n value, is 0.95, this is the pump curve. But when it's 0.8, then you get the equivalent to a smaller pump. So it's actually pretty good. All right, so just remember you can model either centrifugal, regular centrifugal constant speed pumps or variable speed pumps. And okay, so we have force mains in our systems, and they show up in a number of different situations in a wastewater systems. Why would you need one? Well, maybe if there's a drainage divide and gravity is not going to help you and you're not going to drill tunnels through mountains, then you use a force main. If you're replacing a plant that got too old and obsolete, and now you need to take that water and pump to the new plant. If there is a new subdivision that you created, but it can't be connected gravity-wise to the existing system, then you might need to use a force main. If you have a development and, again, not all the users can get via gravity to one desired location, then you bring them all to the lowest point, and then from that single point you pump. Sometimes also if the terrain is very flat, you know, you'd have to really bury those gravity pipes very deep, and it might not get you to the elevation that you need your treatment plant to be. So force mains are very common on flat slopes. So if you're asked, or if you're tasked with designing or sizing the force main and also the pump station, there are a few things that you need to consider. first and foremost, is there a need for pumping? Because as we mentioned yesterday, we always tend to have systems, or we aim for systems that would be gravity fed, so you don't have to worry about spending any money pumping water. So make sure that the need for pumping is there. Then you need to figure out how big, what's the diameter that I'm going to select for my force main. And typically that's kind of the workflow. So you size the force main first, and then you work on the pump details. Okay, what kind of pump is it going to be? Is it going to be constant speed or variable speed? And what's going to be the energy efficiency? Because overall, it's, yes, you buy the pump and that's a big expense, but over time, which is going to be cheaper to operate, right? So energy costs are really a main driver into the decision of what type of pumping you're going to go with. And what kind of station is it going to be? Is it just going to be a booster station? Are we going to just hold water there for a long time? How many pumps am I going to have? Is one pump enough, and then maybe you just need a backup pump? And how big of a wet well do I need? So all those details can be worked out, just kind of in that order. All right, so we figured, we said at the beginning that we size the pipe first, the force main. And how do we go about that? Well, the key design parameter is the velocity. So you kind of know what the flows are going to be, and you know the velocity, so therefore you can figure out the diameter pretty easily. So the idea is that the station should be capable of pumping the peak flow with the largest pumping unit out of service. That is, if you have one or several pumps. And that peak flow, again, that we know, if we've already modeled all the upstream gravity collection system, then we can already have a pretty good idea of what that peak flow is going to be arriving at the pump station. All right, so you figure out your peak flow, you know the velocity, your target, let's say you're going to go with the 5 feet per second velocity in that force main, and that gives you a diameter of X. You know, so you near it to the commercially available pipe size, and then you model that in SewerCAD, and then you see what happens, and you say, okay, well, what would be my system head curve if I were using a 6-inch, that's the pink, or an 8-inch, or a 10-inch, or a 12-inch. So how would you, by looking at this, make a decision? Let's assume that our design flow is 600 gallons per minute. So if you say, okay, I'm going to go, this is my peak flow. Oops, sorry, it's not completely straight. Then going with the 6-inch pipe obviously will be cheaper because it's a smaller pipe, but look at all the extra head losses. So really, you're just kind of wasting energy because you're fighting against that head loss. And if you go on the other side of the spectrum with the 12-inch, which is the red, then it's kind of oversized. You know, you're paying for a whole lot, and basically there are no friction losses right there. The 8-inch will give you, you know, a little bit of head losses, and the 10 a little bit more. So in this case, you might be like, oh, maybe the 8 or the 10. Well, okay, that might be good. This is basically how we decide the force main sizing. Remember that we know our peak flow, we know our target velocity. This is a constant value, so this is how we use the equation to come up with that initial estimate of the force main diameter. So you construct system head curves for diameter. So let's say you got diameter 7-inch, but that's not commercially available. So you might say, okay, I'm going to try it with 6 and try it with 8 and see what kind of results I get. And then you might want to do a curve like this. This is actually showing us the energy versus capital trade-off. So again, we have different diameters here at the bottom, and here we have the different costs. And the blue line shows you the energy costs. So if you see a 4-inch diameter will cost you a lot of energy, right? Because we're just pumping to fight with the friction. But capital, so buying the actual pipe, would be a lot cheaper. 6 would be a little more expensive, but the energy cost would be less. So if you add the values for energy and capital, you get the total cost, which is this black line. And that is a very good way to help you make the decision, because you can see that overall, the 8 or 10 have the best options, right? So might want to actually go with 10, depending on how these projections have been made for how many years. Okay, so what if there are multiple pumps on a force main? Well, sorry. If there are multiple pumps on a force main, then the system head curve that any pump sees depends on what's going on with the other pumps, right? So if the system heads vary widely, you may need to use different size pumps in one station, or use the variable speed pump. So you can see in this graph, we're showing you what happens when only one pump is on, when both of them are on, and when all 3 of them are on. And actually, you can do this kind of analysis in SewerCAD, and it's very neat, because you might find sometimes, surprisingly, that turning another pump on really does nothing, because if you're pumping through a very small diameter, the energy of that extra pump is all to fight the extra friction. So it's very important to do the analysis of the combination of pumps. Okay. Some other considerations. Whenever you're doing this kind of work for wastewater systems, just be aware that the pumps need to operate over a different range of flow conditions, right? Because your flows are not exactly the same one day to the next, and within the same day, it's like at night you get no flows if it's like a residential area, so the pump is just not operating. But in the peak of the day, you might have the pump go on several times. The design and the sizing of your pump is controlled by the peak flow rate, but that doesn't mean that you're only pumping peak flows, right? You're, like we mentioned before, operating over that range of flow conditions. If you happen to have the situation that the wet well level is increasing even when the pump is running, then that's a good indication that something is not completely right? Because even if your pump is on, it's not enough to keep up with the water coming in. All right, so now that we have a pretty good idea of pumps and what things we have to keep in mind, let's see how we model things in SewerCAD and SewerGEMS. There are different options, and when you double click on a pump, you see this called the pump definition, the place where we saw yesterday you input the pump curve. Well, you see here that it says constant power GVF. So depending on what solver you're using, there are some types of definition that are not available. So you notice that if you're using the GVF solver, you get a lot more options. If you're just using the dynamic wave, you have fewer options. For the GVF solver, typically you might use something like a standard 3-point. Basically, you need to enter this point, and this point, and then based on that, the software will calculate the entire curve. The 3 points are the shut off head. So when you have 0 discharge, what would be the pump head? The design point, and the maximum operating point. If you're just doing design at first and you don't really have a full catalog and you don't want to input all those details, then you can just input a 1-point curve, and the software uses these values to complete the curve for you. So how did SewerCAD come up with all those points? Well, those values that we were looking at come from a full set of equations that I thought were here, but we don't. But this comes from a typical pump curve, so it's pretty standard and accurate. So if you do go with this, then it's okay for the original design, but once you are like said that that is the design point that you want, then what you want to do is going to the manufacturer, get a real catalog, and input all the points along the curve, not just stick with the 1 point. There's another type, which is the standard extended, which has basically you input these 3 points, and we just extrapolate, or SewerGEMS extrapolates all the way down to 0 head. There's a multiple point as well, where you input an unlimited number of points to make it as close as you can to the real curve. There's also positive displacement pumps. Those are the ones I once was at WEFTEC, and I really had never seen one of these pumps before, but the guy who sold it explained it to me as like it's squeezing toothpaste. And really that's what it does. So that's what the positive displacement pump. They're typically used for pumping solids, and because it's like it's a mechanism pushing that toothpaste out constantly, they will pump a fixed flow regardless of the head, right? So if you have to model that, you can use what we call the multi-point curve and use a very steep slope, like what you're seeing there. Okay, so any of those types of pump inputs that you've decided to use, you got your pump curve. Now what? Now you need to tell the software what triggers a pump to go on or off. The controls are a little bit different again in the GVF-Convex solver. So if you want to be like timing it, like say it goes on at 6 a.m., off at 10 a.m., etc., or the trigger is maybe the flow in mount pump. If you have very complicated controls, or unusual, let's say, not necessarily complicated, then the GVF solver gives you more options. But traditionally, a pump is controlled by the wet well level. So when it's really full, turn the pump on, and as it empties the wet well, turn the pump off, and then wait for it to fill and go on. Okay, so wet wells, again, most of the time control the pumps, but if you needed to do it differently, you could as well. So what about a wet well? What is a wet well? Well, a wet well serves a number of functions in a system. First is providing that head at the suction of the pipe of the pump. Remember, we said we never want to have, we need to have a good head at the suction end of a pump, so there is no cavitation. So that's purpose number one. Purpose number two excuse me, is to avoid us having the pump be on all the time. So, collect, and when there is enough, we pump for a little bit. Okay, so storage is a very important function. If you're turning your pump on and off, and it's a constant speed pump, obviously, because the thing with variable speed pumps is that they don't really need a wet well, right? Because a variable speed pump is always on, so you don't really turn that pump off, and you don't really need that storage. So they are very important when we talk about constant speed pumps. And how big of a wet well it needs to be? Well, how many times do you want to turn the pump on? And again, that every time you turn that pump on is going to cost. So do you want to turn it 100 times in a day, or maybe only 5? It is all directly related to the volume of that wet well, how big you're going to make it. Okay, we talked about this yesterday in a graph, that when we're running the SewerCAD solver, we kind of, or the SewerCAD breaks it into subportions, the gravity and the pressure. And how we go back and forth between gravity and pressure is, if you go from gravity to pressure, typically what you have is a wet well. And that accumulates the flows until you can pump them. And the wet well can be a fixed wet well level or a variable wet well level, depending on how you're running it. There's something I'm always very hesitant when I explain this, because when you're running this solver, and if you run it in an extended period simulation, there's no problems. You know, it will tell you how much the water goes up or down in the wet well and how much is being pumped at any time step. So in EPS, there's no problem. But when you're doing steady state calculations, there's an option in the SewerCAD solver to use or not use pumped flows. Okay, the default is conserving pumped flows, which means it will assume that whatever incoming flow is coming into the wet well will be pumped out. So it just kind of ignores the pump. It says, oh, I'm assuming that I will get a pump that will be able to pump it all out to my outflow. Or you can do the conserving loads, which is actually using the pump curve. So we will actually do the workshop today where we use these two different configurations, and you get to see how it works and if you would ever need to use one. Like this, the conserving pumped flow. Okay, and why do we have that option? Well, because if you look right at the arriving end of the pumped flows, you're going to see something like this. You're going to see the discharge being like, there's no water, there's no water. Ooh, pumped flows, and then no more flows. Oh, the pump is on. Flows. Pump is off. Pump is on. So you see that right near the pump, right? But if you start moving downstream in the gravity system, you're going to see that there is attenuation. So you no longer see all these very strong peaks. It just kind of mellows into something like that. So that is the assumption as to why you might want to do conserved pump flows, because really further down the stream, you're not going to be seeing these pumped flows, but rather the attenuated flow. Okay? All right. Another consideration that might happen is high points. Intermediate high points are actually a little bit difficult to design and model, because if there is no air release at the high point, your system can behave as a siphon at some times. But the problem with this is that gases build up wherever we have these high points, right? So what do people do typically? They put an air release here. Why? Because an air release stops the siphon from happening. So if you do put an air release, then you see basically the hydraulic grate line shows this break, let's call it a break here, and it would be more accurately representing what you'd have in the system. If you have a high flow, then your pipe is going to be full. But if you have low flows, then your pipe is going to be partially full. Okay. So pressure sewers. I'm missing a picture here. I had a student once last year, and he actually worked for a company that manufactured these grinder pumps, and he refuted some of my claims, and I promised I would put a picture of his pumps here, and I don't have it in this presentation, so I'm sorry. But basically, the pressure pumps is they're individual grinder pumps located typically on the basement of each customer. And the reason you put them there is because maybe it's a very rocky area where it'd be really expensive and hard to excavate and put gravity sewers. Or maybe there's no slope. Maybe you're at a lake or something. You don't want to really even contaminate or have the possibility of contamination. Or maybe your customers are so far between that, laying a big pipe would be costly and manholes, and also you decide to do a pressure sewer. So the advantages are a lot, right? Lower cost of installation because the pipes are smaller. You don't have to excavate as much. Gives you flexibility in the routing of the piping. It doesn't matter if topography goes up or down, pipe flows don't care. You don't really need to put all those manholes. There's not going to be infiltration and inflow. But the disadvantages are there, and of course everybody that is running those pumps is incurring into electricity costs, maintenance. If the power is gone, then you're not going to be able to pump your sewage out of the house, so that's a problem. You have to maintain that. And another disadvantage, actually, which is what I was talking to that student about, is that people sometimes would flush like those flushable wipes that are not really flushable, and that could clog the pumps. And his pumps, actually, it was very impressive. He shared with the whole class a YouTube video where we could see the complete diapers and gloves and you name it completely gone through these grinder pumps. So now they make them really good quality, so that is no longer a disadvantage. All right, so let's say that you're doing a project and you decide, I'm going to have to go with this kind of grinder pumps. What are you going to need at each location? A storage tank, a pump, and a service line. And then, down the streets, pressure sewers. At the high points, you will put the air release valves like we talked about before. And then finally, they would discharge, hopefully to a manhole where then they will flow gravity to your treatment plant. Okay, so if you're doing that, how do you estimate what kind of flows you're going to be seeing? Typically, 50 to 70 gallons per day are used. And, but again, it really depends, so don't take that with a grain of salt. One thing that you will notice that the difference between the peak and the average flow rates for these kind of systems is much larger than it is for gravity systems, because it doesn't naturally flow, right? Basically, the flows are when all the grinder pumps happen to go on at the same time, and then maybe no flow from the grinder pumps. So that is what makes that difference be so large. Here's a typical equation that you might want to use if you're trying to figure out the peaking factor for those pumps. By the way, you guys you received these PowerPoints as well, so don't worry about writing down all these equations. You are getting that in a PDF. Oh, you did get it actually already. Okay, so you decided that you are going to go with this. How do you model it? You can at each residence, draw an individual pump and a tank, and then enter the individual pump curve, the elevations, the volumes, and that could be, you know, okay if you have 5, 10, 15 houses, but if you have 200 houses, you know, it's a lot to input and to work. So you could do an intermediate level of detail where you would represent a house connection as a known inflow as in an extended period simulation. So rather than entering the pump curve and the pump controls and all that, you simply say, okay, at this house, this is what the inflow would look like. And you just enter a flow versus time inflow. So if you're doing the individual pumps, then again, you need to know the triggers. And if you're trying to figure out the pipe sizes, then you can combine the loads at a few nodes rather than doing it individually. Here's an example of how it's done if you do the modeling of a tank and a pump at each residence. So we have a house tank, we have a grinder pump, and at this junction we have the inflow, the incoming flows. Notice that this is a pressure junction. So this is very similar to kind of what you would do if you were doing it with like SewerCAD, SewerGEMS. Okay, so to finalize this pressure presentation, remember to always use pressure junctions and pressure pipes when you're doing a pressure system, because sometimes people forget and you put a gravity pipe and then you can't really connect it to a pressure junction and things like that. Again, we always recommend that you use the GVF-Convex solver for pressure sewers and anything pressure. If you find that you need to switch between, if you're using SewerGEMS and you need to switch between solvers, then so that you don't have to replicate work, use a multi-point pump curve definition that can be used for both solvers. If you have a very large system and you have lots of pumps, if you model a lot of the individual pumps, it can be cumbersome and complicated for the computational engine. So to save yourself some time, don't do the individual pumps, just do the inflow curve. And include the most important air valves that you have in the system. And as every time you do model of pressure systems, one thing you always want to keep an eye on is the velocity when you have high flows, because pipes that have high velocity is what we call bottlenecks. So maybe you're wasting your pumping energy in those bottlenecks in the system. So look for those and upsize if possible. All right.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.